Welcome. In today's video, we are going to look at the maximum likelihood estimations, or the estimators, for the Pareto distribution. To begin with, let us set up our problem. So suppose we have a series of random variables, x1, x2, all the way up to xn, which are all independently and identically distributed with a Pareto distribution with parameters alpha and lambda, where alpha is the shape parameter and lambda is the scale parameter. So the PDF of xi is given by the following. We write it as f subscript x, xi given the parameters alpha and lambda is equal to alpha lambda to the alpha over xi to the alpha plus 1, where xi is greater than or equal to lambda. Notice this condition here. Now, from this particular definition, I just want us to introduce this new concept, not new necessarily, but the idea of an indicator function, because we can rewrite this PDF in a slightly different format that's going to help us later on when we derive the maximum likelihood estimate. I'm going to rewrite this as alpha lambda to the alpha all over xi alpha plus 1, and I'm going to put it an indicator function, and I'm going to call it indicator function I greater than or equal to lambda, and then I'm going to say xi is an element, in this case, of R. Now, why have I written it in this form? Well, the indicator function, xi less than or equal to lambda, takes really two values. It takes a value of 0 and 1. And it takes the value 1 when the statement inside the indicator function is true. So in this case, when xi is greater than or equal to lambda, and then by virtue of the fact it takes 0 when the statement is false. In other words, it will take 0 when xi is less than lambda. And by virtue of how this definition works, this PDF here is equivalent to the PDF above that we have. So, let us now derive the likelihood function. So the likelihood function, L subscript n, of the parameters alpha, lambda, given our vector of data x, noting that x is equal to a vector of observations x1, x2, all the way to xn. Well, the definition of the likelihood function is the product of I equals 1 to n of all the individual probability density functions evaluated at our particular data points. Then, again, I'm just going to rewrite this. This becomes, this again, still the product, I equals 1 to n. I'm going to take our version here that we have, and I'm going to copy this down here, paste that down here, just remove that negative sign that somehow came through, and this becomes our product. Now we can use, or we're going to note that we can distribute this, given that every item here is a product or is getting multiplied by each other or dividing by one another, we can actually distribute this product in some sense. And so that's what we're going to do. First way we can distribute the product is we can note that is the product of I equals 1 to n of all the alphas times the product of I equals 1 to n of all the gamma alphas times the product of I equals 1 to n, and in this case I'm going to say the xi to the power of negative x plus 1, so that's just, I've just put this in a negative power format, our denominator there. And then the final component that we have is we still have the product of all these indicator functions, xi greater than or equal to lambda. Next step is to recognize, now, when we take a product of I equals 1 to n of a series of alphas, although there is no dependency on any index I, it does, however, mean we need to multiply alpha by itself n times, because there are a total of n indices in that product. So that just becomes alpha to the power of n. And similarly here, when we've got our lambda alpha, again, no dependency on indices, but we are doing it n times, so then we can rewrite that as lambda to the alpha all to the power of n. Now, in this particular instance, we've got, what I will do is I'm just going to actually simplify, or I'm going to expand the terms, just so it's a little bit more clear about my procedural steps, so it's easier to follow. So in this particular instance, we've got, I'm just going to expand it here, and I'm going to say that's x1 to the power of negative alpha plus 1 times x2 to the power of negative alpha plus 1 times dot 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 times xn to the power of negative alpha plus 1, close the bracket, and of course that's that part expanded there, and now I'm also going to expand the indicator functions out as well. So quite simply, that next component is the indicator function x1 greater than or equal to lambda times the indicator function of x2 greater than or equal to lambda times dot 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 times the indicator function that xn is greater than or equal to lambda. Okay, let's do a bit more simplification here. So a to the power of n, or alpha, sorry, to the power of n, stays as alpha to the power of n, no tricks there. Alpha, in this particular instance, I'm going to take that in and I'm going to distribute it inside the power. So using our power laws, that becomes lambda to the alpha n. Now, using our power laws here for this component of the expansion, what I note here is that because we've got the same power multiple times, we can actually rewrite this this product as x1 times x2 times dot 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 times xn to the power of all to the power of negative alpha plus 1. And then we've got a times still, and this is a very important fact here down the bottom when we're trying to simplify the indicator functions. So indicator functions, remember, are a binary sort of function where it can take either a value of 1 or a value of 0. So in this particular circumstance here, we can either have, for each of these indicator functions, we can have 1 or 0. Now, if any of those indicator functions is equal to 0, say this indicator function here, then the whole element or the whole product collapses to 0 by virtue that anything multiplied by 0 is 0. So this particular instance can actually only take two values, either 1 when all of them are equal to 1, or 0 if any of them are equal to 0. And so we can actually rewrite this indicator function, the product of indicator functions, as one indicator function. And that product is simply x1, or the condition in the indicator function is that x1 is greater than lambda, x2 is greater than lambda. In fact, all of the data points are greater than lambda for this to hold true. And then that is the equivalent indicator function, because if all of these are true, it's equal to 1, and if one of them doesn't happen to be true, then it's 0, as with the one above. So moving on to hopefully what ends up to be the last step in our product here. It just got alpha to the power of n, gamma of alpha n. In this particular instance, our product of the x1 and x2 to xn, I'm going to just rewrite in this nice compact notation as the product of xi's all to the power of alpha plus 1. And then in this indicator function, what I'm going to just simplify it down to, and this is a really nice simplification, is that if each data point has to be greater than lambda, then this is the equivalent that, what I could say is, it's the equivalent that x subscript brackets 1 is greater than lambda. In other words, recall that x subscript 1 is a statistic of the data set, and it is the minimum value of the data set. So if the minimum value of the data set is greater than lambda, then all of that is true. So that is just a simplified, nice version that we can use. Cool. So I'm just going to take a copy of this with my the software that I'm using. And now that we've got this simplified version of the likelihood function, we're going to move to the log likelihood function. So little ln, the log likelihood function of alpha lambda given our data set, is by definition the log of the likelihood function, which in this case is log of, and I'm going to rewrite that, and I'm going to paste in our version of the likelihood function that we derived just previously. And now I'm going to do some bit of simplification here of our products. So the first component to note is we've got a series, or the first thing to note is we've got a series of products in this particular function, and we know that log of a series of products is equal to the sum of logs. So we can rewrite this first step as log of alpha to the n plus log of lambda to the alpha n plus log of, and I'm going to be careful here, the product of I equals 1 to n of xi all to the power of alpha plus 1. And then finally we've got the plus the log of the indicator function x1 greater than or equal to lambda. Again, we're going to do some slight simplification here, and we're going to notice that we can use a power law, or a log of something to a power. You can bring the power down the front, so that can be simply written as n log alpha. Similarly, we can do something here with the lambda to the power of alpha n. That becomes plus alpha n log lambda. Again, something similar here with the powers of the negative x, or you've got a negative power here that can come down the front. So that becomes minus alpha plus 1 log of a product of I equals 1 to n of xi. And then we still have our original log function of the indicator. And for now, I can't really do any simplification to that. Continuing forward, we might do one more added bit of simplification here. And that's just this component here where we've got log of a product of xi's. And recall that when we have log of a product, it's the same as the sum of logs. So I'm just going to rewrite this again. Log alpha plus alpha n log lambda minus alpha plus 1. And then this becomes quite simply the sum I equals 1 to n of log x, log xi, plus, and then we've still got our log I x 1 greater than or equal to lambda. Now, traditionally, or actually, I might do one extra nice little simplification here before I go on. And I'm going to copy that, and I'm going to take exactly the same step, except instead here, I'm going to define a new sort of term just to the side so that we're all familiar. And it's going to be log x bar, and the bar is on top of the entire log. And I'm going to define this as 1 on n sum I equals 1 to n log xi. In other words, it defines the average value of the log of our data set. So in this case, where I have instead log xi, the sum of log xi's, I can actually rearrange this equation in green down the bottom for a sec and multiply the n to this side of the equation. And this gives me that n times the average value of the log of the data set is simply equal to the sum of the logs in the data set. So in this part here where I've got the sum of log xi's, I'm going to rewrite that as n. Maybe I might do it in white so it's consistent. N log x bar here. And that's where I'm going to stop with the log likelihood function, at least in terms of simplification. So now that we've derived our log likelihood function, recall that one of the aspects is to maximize the log likelihood function, at least to determine the maximum likelihood estimates. Now, traditionally, we might use calculus, and we differentiate the log likelihood function with respect to parameters. And we will use that, for the parameter alpha. But for the parameter lambda here, we're actually going to use some observations, or some logic here without having to differentiate with respect to lambda. One, because it actually wouldn't work in this case, but two, because we also want to avoid unnecessary work. So there are sort of two observations that I want to make here. Ignoring this log component for a second, if we just have a look at this element of the log likelihood function, we note that to maximize the likelihood function, sorry, the log likelihood function, alpha, gamma, given our data x, then we need this condition to be true. We actually, in terms of alpha, we actually need, sorry, in terms of lambda, apologies, we need to maximize the component that depends on lambda. And there's only one component that depends on lambda, at least ignoring the log down here, and that's this component here. So we actually need to maximize, alpha n log lambda, which is actually the equivalent of maximize lambda, because the log function is a one-to-one function which is continuously increasing in terms of lambda. So that's observation 1. To maximize the likelihood function, we need to maximize the value of lambda. There is another thing we need to note here, because I said ignore the log for a second, but now we're actually going to also have another condition. We need to maximize the log of I 1 greater than lambda. Now, in this particular instance, remember the indicator function can only take two values, 1 and 0. Now, if it takes a value of 0, then you take log of 0, which is sort of undefined. But if we were to really sketch out a just a quick version of what a log function looks like, just on the side here, just to understand, as you get towards, again, this is a log function, I'll call it y equals log of x on the side and x. If you were to approach 0 in this function, as you get closer and closer to 0, this would basically blow out towards a negative infinity. It would diverge towards negative infinity. So we definitely don't want a negative infinity here, because we want to maximize. We don't want to minimize, we want to maximize. And so we want to maintain the condition that I is equal to 1. At least when I is equal to 1, you get log of 1, which just collapses to 0. You avoid this divergence to infinity. So, keeping that in mind, we can say that is the equivalent of I of, or x subscript brackets 1 greater than or equal to lambda is equal to 1, which by definition is the condition that lambda is less than or equal to x1. So we've derived two separate sort of logical statements about lambda here from our formulation of the log likelihood function. Now, putting these together, we need to, 1, maximize lambda, but also we have the constraint that lambda has to be less than or equal to the minimum value of the data. And so putting these two together, we actually end up with the following condition. Lambda hat has to equal the minimum value of x in order to maximize the likelihood function. And that is how we derive the first element, or the first maximum likelihood estimate. Now we go on to deriving a maximum likelihood estimate for alpha, which we are going to do using the usual techniques. So the first thing I'm going to do is I'm just going to take a copy of the likelihood function, copy that, and I'm going to take it to the next page. And I'm going to use it here to do some calculations. And we'll put that there for now. So let's have a look at how we're going to do this. So the partial derivative of the likelihood function, the log likelihood function, with respect to alpha in this particular case. So we're going to use calculus now to determine the maximum likelihood estimate for alpha. Is again, we're going to take the partial derivative of the entire likelihood function with respect, log likelihood function with respect to alpha. So for the first component here, n log alpha, we know that the derivative of log of a variable becomes 1 over that variable. So then first component is simply n on alpha. Next part here, we have alpha multiplied by a constant with respect to alpha. So when differentiated, we just end up with n log alpha, the constant. Sorry, n log lambda, the constant. And then here we again have something sort of similar where we've got alpha times a constant. So when differentiated, we again just get that constant. But in this case, the constant has a negative out the front. So I'm going to write n log x all bar. And then the final term here, we note, actually doesn't depend on alpha at all. So we can just ignore it to get all together and it disappears to 0. The next thing, of course, we're going to do, recall, we're going to take the second derivative of the log likelihood function with respect to alpha, and that's going to help us at least with the second derivative test when we need to prove that it's a maximum. So in this particular circumstance, the final two terms here don't depend on alpha at all. So they collapse to 0. And then when you differentiate n on alpha, that is the equivalent of d on d alpha of n on... Well, firstly, let me write, it's the derivative of the first derivative. So n log lambda minus n log x bar all of the bar. The first thing I'm just going to note is, however, I'm going to rewrite this as n alpha minus 1 at the front here, just to note that when we do differentiate something to a power, what we end up with is we bring down the power, or we take the power down the front, minus 1 times n alpha to the negative 2, or quite simply negative n on alpha squared. And then that's the second component. So to find our alpha hat, or our maximum likelihood estimate of alpha, we note that the derivative of the log likelihood function, given the data evaluated at alpha lambda is equal to alpha hat lambda hat, must be equal to 0. That's how we determine our value of alpha hat lambda hat. So I'm going to take our derivative here that we computed, copy, I'm going to paste that down here, and instead now I've got to evaluate it at lambda hat, so I've got to put alpha hat lambda hat is equal to 0. Going to do some rearranging here. This means that if we rearrange the equation, we'd have n over alpha hat is equal to n log x bar minus n log lambda hat, which we actually have already derived. So lambda hat I'm going to replace instead with x subscript 1. And then we've got just one extra additional line of simplification here. That becomes alpha hat is equal to, rearrange the equation, move the alpha to that side, divide both sides by the component that's not dependent on alpha, and that gives us n on n log x all bar minus log n log x1, put the vinculum there, and then finally we've got the fact that the n's cancel with one another at the bottom, or you can take n out as a common factor from the numerator and the denominator, and then that finally leaves us with alpha hat is equal to 1 on log x bar minus log of x1. Complete the fraction. And there you have it. We've derived the maximum likelihood estimate. The final thing to note, however, is we need to show that it's a maximum. And just to show that it's a maximum, note that the second derivative with respect to alpha in this particular case, alpha squared, is equal to, we derived it before, negative n on alpha squared, which is less than 0 for all values of alpha, an element of 0 to infinity. It's actually true for all values of alpha in the real number line, less excluding 0. But alpha, our parameter, can only take values between 0 and infinity anyway. So I've written it as such, and so that proves that alpha hat is in fact a local maximum. And so there you have it. We've derived both the maximum likelihood estimate for alpha here, which is given by this particular function, and we also derived earlier the maximum likelihood estimate for lambda, which was on the previous page using some logic.